Hello, good evening. I'm Krishna Kumar, and today we're going to learn about the midpoint theorem as applicable to triangles. The midpoint theorem, and what does the midpoint theorem explain to us? Well, in this case, let me first draw a triangle. Right? This is our triangle ABC. Right, we just mark the vertices A, B and C, right? So if I mark midpoints of AB as D, that of AC as E, and I join D and E, so what does result here? So here I'm given a triangle ABC, I'm given midpoint, so let me mark AD as being equal to DB, let me mark AE as being equal to EC. So what does midpoint theorem state? It states that the line joining these opposite sides is parallel to the base and its magnitude is equal to half the magnitude of the base. So how do we end up proving this? Well, it's pretty simple. Let me just make some space for some construction here. So, well, how do you prove this? So firstly, you extend DE to a point F, right, such that the length of DE is equal to the length of EF. Then you join CF. Well, now what do you see between this triangle AED? Let me just draw this clearly. AED, this is your point E, right, and CEF. Well, this is a clear-cut case of an SAS congruence. That is, my first step of this proof would be in triangles AED and CEF. So what I have here is angle AED is equal to angle CEF being vertically opposite angles. I'll abbreviate it as VOA, right? And I have the corresponding sides AE being equal to EC, which is given to me, and as well as I have DE being equal to EF, which is by construction. So this proves the congruence of these two triangles, that is, triangle AED is congruent to triangle CEF. So what results from proving this congruence, you might ask? Yes, for one thing, my eventual aim is to prove that BCFE is a parallelogram. So what do we end up having to prove? We have to prove that DE is parallel to BC and that DE's magnitude is half of BC. So if DE has to be parallel to BC, then it's obvious that somewhere around the line you have to prove that BCFD is a parallelogram. And let's now think back to the definitions of a parallelogram. So a given quadrilateral is a parallelogram if two sides are parallel, right? It's the most basic definition. So when would two sides be parallel? Either when it is already given, or if there is a property of lines being cut by a transversal and you can get the alternate angles equal, then you can say the lines are parallel. So you observe here, if you observe here BD, right, and in these triangles, once we prove the congruence, so there are some relations of CPCT which are applicable, that is corresponding parts of congruent triangles. I can easily see angle ADE, right, would be equal to angle CFE, right. The moment this is true, you know that if AB and CF are intersected by a transversal DF, then these angles are nothing but alternate angles. So immediately I shall write here that AB is parallel to FC, or since BD is nothing but a part of AB, so I write here that BD is parallel to FC, right? Now the another CPCT relation which comes through here, let me just write the CPCT relations here and enumerate them. This is the first one, and the other one is AD equal to CF, right? This also follows from CPCT. Please note the order in which I have written the congruence of the triangles. A and D both are the first and third letters in this particular triangle denotation. C and F are similarly respective in the respective locations in the other denotation. So AD would become equal to CF and angle ADE would become equal to CFE, right? So now what do you observe? We've been given here, let me just write what is given here, right? Just to make things more clearer here. See, I've been given that since D is a midpoint of AB, so AD is equal to DB. I'm also given, let me just write this as B, right? I'm also given AE is AC, right? So if AD is DB and AD is CF, so what follows immediately is a very important conclusion. So that means that DB will be equal to CF. So here we have BD being parallel to FC and BD being equal to CF, which immediately gives us enough criteria to say that BCFD is a parallelogram, right? So this particular quadrilateral, like abbreviated as parallelogram, right? So it becomes a parallelogram. So in a parallelogram, you always know that either one set of sides, both sets of sides are parallel, or there are some more refined definitions like one set of sides is parallel as well as equal, or we could say the diagonals of a particular quadrilateral bisect each other. It is condition enough to say that the quadrilateral is a parallelogram. So now if DB is parallel to CF, let me now look at the other two sides. This implies immediately that being a parallelogram, I can now write that the other two sides DF would be parallel to BC, and not just parallel, it would also be equal to BC. So DF would be equal to BC, right? Now here's where the entire midpoint theorem is proved. Now DE being a part of DF, then therefore would be parallel to BC. And what do you see here? DF, let me now write it as in terms of its component lengths, that is DE and EF, right? The sum of them these segments would be BC. But please remember my construction here. My construction was to extend DE to F such that DE is equal to EF. Let me just write this here to make things clearer. My construction here was to extend DE to F such that DE is equal to EF. So using this information, so in this equation what do you see? You see DE plus EF being equal to BC. So can I write this as 2DE? Yes, I can. Which is exactly what I do here. Write this as 2DE being equal to BC, which implies the second result of the midpoint theorem, that is DE is half of BC. So this proves both the facets of the midpoint theorem. Now we'll try and solve a question with regard to this. So how about an example? So if I give you a trapezium. A trapezium is, of course, you know, a quadrilateral which has one set of sides as parallel. So here you have A, B, C, D being a trapezium. Let me denote AB as being parallel to CD or DC, right? Now here's where what I do is I mark midpoints of AD and BC. Let these midpoints be X and Y. Now if I happen to join both these points, so what I need to prove here is, can I now prove that XY is equal to half, right, DC minus AB? Can I do that? Now that's the challenge here, and I shall use the midpoint theorem to do this. Well, any ideas here? First thing I'll do is I'll write what is given as in any geometrical proposition. I am given that AX is equal to XD. I am given that BY is equal to YC, right? And of course ABCD is a trapezium, right? which means AB is parallel to DC. It's a trapezium with the parallel sides being AB and DC. So now what I do is I do a rather different kind of construction. I actually join A to Y and I extend it, right, to meet DC produced at a point. Let this point be, say, E, right? So what do you observe here? Well, my main aim here is, see, I need to prove that I need to find a relation between xy and the base. So if I'm able to get a relation of where y stands, and if I need to use the midpoint theorem, so I need triangles. So what I've done is I've actually created a triangle, and a triangle which is going to help us prove this is triangle ADE. Now I already have here that AX is equal to XD. So if I can prove that AY is YE, don't you think I can immediately concur from this that XY would be half of DE, right? And XY would be parallel to DE, which would help us in a long way. So if I now get a relation between, now DE has two components, one being DC, which is what we need to prove XY in terms of, and the other component is CE. Well, how does this C come into the picture? Yes, I need to now prove a congruence of triangle AYB and EYC. Now how would they be congruent? So these are the triangles AYB and triangle EYC. Well, what do you observe here? I got a couple of parallel lines AB and CE being intersected by a transversal AE. So what are angles BAY? Angle BAY is clearly equal to angle CEY, isn't it? Let me just check the order in which I've written. Yes, these are, of course. Please remember, it's always important to write the order of letters when you're writing a congruency relation. If you make a mistake in writing the order of letters, your entire corresponding part relations would be wrong and you would end up with a very wrong conclusion. So please be aware of the order in which you write any congruence relation, right? In geometry, it's always pays to be a bit patient and take your time. So this is one of the relations. Other being, you see a pair of vertically opposite angles, AYB being equal to angle CYE. Now I'll just write these as vertically opposite angles. And so in congruence, of course, if you have two angles, there's got to be a side. So which side shall I pick? Oh yes, I'm given here BY equal to YC. Wow, how convenient. So here I have a case of which congruence is this. Let me just mark the equal angles to show you. BAY is this angle being equal to CEY. Got a pair of vertically opposite angles here. And I got a side. Now which side is this? Is this included or non-included? It is a non-included side. Let me write the side equality relation, which is BY is equal to YC, which ends up in letting us know that triangle AYB is indeed congruent to triangle EYC, and the congruence relation which we use here is AAS. What does result from this? Yes, the two most important relations are the side equality relations. So let me write the CPCT relations here. First one being that AB, right? AB should be equal to EC. Please note, A is the first letter of AYB, B is the third letter of AYB, E is the first letter of EYC, C is the third letter of EYC. So that's what I was mentioning. It's always important to write the letters of congruent triangles to be in the order, in the right order. In this case, since it was AAS, you had to write whichever angles are equal of both the triangles. In this case, of course, BAY being equal to CEY, it had to be that A and E there had to be a correspondence between A and E. BYA was equal to EYC, so there was Y had to be in the same place, which in this case happened to be the second place. Third place automatically be occupied by the third vertex. Now the second CPCT relation I get here is that AY is equal to EY. Wow, what a relation. Now please observe triangle ADE. In triangle ADE, I have I have x and y being midpoints of two opposite sides. Let me just mark AY as being AY is now equal to YE. So in triangle ADE, I have AD and AY are two opposite sides, and X and Y are midpoints, right, of two opposite sides. So what does it tell you? Think back to the midpoint theorem. Midpoints, right, of uh, two opposite sides AD and AE. So it's another clear application of the midpoint theorem, right? So what do we prove here? Some very interesting results we get here. That is, firstly, xy has to be half of DE, right? And the second relation we get is xy is parallel to DE, which we shall not require. In case it was asked to prove here that DC by X was a trapezium, yes, it is a trapezium, since this particular criteria, it qualifies this quadrilateral to be a trapezium, right? One pair of opposite sides are indeed parallel. But here we are asked to prove an equality. So now let me express this equation xy equal to half DE in terms of its components. So xy is half, I write DE in terms of DC plus DE I shall write, and so DC plus CE, right? Now if you notice, what is CE? CE is nothing but AB. So this gives us our relation that the line joining the midpoints of two opposite sides of a trapezium is equal to the sum of the two, half the sum of the two parallel sides. So we ended up proving this using midpoint theorem. So we just write here to prove this, right? This is plus, right? So this was one application of midpoint theorem. Well, now you would wonder that there would be cases where you would have to prove the converse of the midpoint theorem. So what does the converse of the midpoint theorem state? Well, the converse states quite the opposite. Converse means the opposite. So as a converse of the midpoint theorem, right? Converse of the midpoint theorem, well, it would say that if I have a triangle, this is my triangle here, and in this triangle ABC, if I mark a midpoint of AB, say D, right, such that AD is DB, then I draw a line parallel from D, right, DE, say, which is parallel. Let me just mark these as parallel lines. So the given conditions here are that AD is equal to DB, right, and DE is parallel to BC. So what are we left here to prove? We are left here to prove that AE has to be equal to EC. So let's set to prove this, and let's solve a question on this as well. So I'll just make way for a new diagram here. Right, here's my triangle ABC, and this is my triangle ABC, and it follows quite a similar proof. In fact, it's a bit more easier than the earlier proof. So here's I created my triangle again, joined the line here, mark AD equal to DB, DE parallel to BC. Let me just extend DE to, rather than that, well, don't you see we already have two sides parallel here? So what does it tell you? Can't I just create another line parallel to BD to actually make a parallelogram? Yes, I can. So I just draw CF parallel to BD. Now here's where I get a parallelogram, right? So the construction here is I draw CF parallel to BD, right? So what results is that in quadrilateral, now this is important in quadrilateral because this forms a major part of the proof. So in quadrilateral BCFD, I get to notice here that DF is parallel to BC. Now why is that? Now that is because DE is parallel to BC and DF is nothing but an extension of DE. Now this is given, and the other pair of sides, that is BD, is parallel to CF, which is by construction. So therefore, by the very basic definition of a parallelogram, I can then prove that BCFD is a parallelogram. So, right, so once it's a parallelogram, now my main method here would be to prove triangle AED to be congruent to CEF, by virtue of which we get a CPCT relation relating AE and EC. That's my main aim here. Now to do that, I already have a set of parallel lines, don't I? I know that BD is parallel to FC. Now these are being intersected by a transversal DF. So what do you see? If you see some alternate angles here, yes, angle ADE and angle EFC, yes. And what else do you see? You see a pair of vertically opposite angles, yes, right? And what else? Well, if it's a parallelogram, obviously the opposite sides are equal. So what follows from this quadrilateral being a parallelogram is that BD is equal to FC, right? Then you write, but BD is nothing but AD. So from these two relations, I can write that AD is equal to FC, which is a very important relation here. So how do I use this to actually prove a triangle congruence? AD is FC. So which particular congruence criteria do you see here? Yes, again AAS. So since I have these three criteria, I can immediately conclude that triangle AED is indeed congruent to triangle CEF by the AAS congruence criterion. So therefore by CPCT I can conclude that AE is CE. Please always note again, I repeat this, that the order in which you write the congruence relation is always of a lot of importance, because if you write the order of congruence is incorrect, your CPCT relations will not turn out to be correct, right? So AE becomes equal to CE, which proves the converse of the midpoint theorem. Well, shall we do some questions on this? Okay. So for this, let's think of, suppose I give you a question, say, okay, suppose we are given here, say a parallelogram, right? And right now, suppose what I do here is, now let this parallelogram be ABCD, okay? Now, what I do here is, if I just mark a midpoint here, say E, and if I draw a line parallel, well, a line EF which is parallel to DC. Now, can I get some relations here? Well, can I get some proofs out of this? Well, let me first mark these lengths to be equal, right? Now, if I want to find a particular relation, let me join AC over here, right? So now if AC intersects EF at the point O, so what do you observe here? So I can apply the converse of the midpoint theorem. The first thing I write is, I know that ABCD is a parallelogram, right? I also know that AE is equal to ED, and I know that EF has been drawn parallel to DC. So in triangle ADC, first I shall apply the converse of the midpoint theorem, right? So what do I get? Applying the converse of the midpoint theorem, which I shall abbreviate as NPT, I get that AO is equal to OC, right? Let me call this as relation 1. Now what do I get here? Then I get, now let us look at this triangle, triangle CAB. Now, triangle CAB, I know that CO is OA, right? I also know that FO is parallel to AB. Now why is that? Right? Let me just mark these lines as parallel here. Since it's a parallelogram, AB is parallel to DC and so is EF. So EF is parallel to both these lines. So in triangle CAB, I have a clear condition here that OF is parallel to AB, and also O is the midpoint of AC. So again, by applying converse of the midpoint theorem, well, do we get interesting relation here? Let's see. So this lets us get a result that BF is equal to FC. So what this tells us is that if in a parallelogram, if I were to draw a parallel line from the midpoint of one side parallel to the base, then it bisects the opposite side, right? So that's an interesting result. Of course, you shall study many more such riders in geometry. Well, so this was a brief introduction of midpoint theorem. It was a real pleasure talking to you students, and my name is Krishna Kumar. I work at Resonance Mumbai, and well, it shall be a pleasure to again have interaction with you all. Thank you so much. Thanks. Bye.